Hello, today we're going to talk about circular motion, which is the sixth topic in the IB physics series. In fact, in the whole topic we're going to talk about circular motion and gravitation. But let's start with circular motion. Well, first let's draw a diagram of something moving, of an object moving in a circle of radius r. So here we go, here's my circle, has a center, and I have an object. Let's make it a blue object moving around in this circular path, and the circle has a radius little r, and the object is moving with a velocity v in that direction. Now notice, as the particle moves around the circle, its velocity changes direction. At this point, this velocity vector is pointed this way. At this point, its velocity vector is pointing this way. And at this point down here, its velocity vector is pointing this way. So we know that because the velocity is changing, there must be an acceleration. And we're going to come on to that in a second. First of all, let's define the speed at which this particle is traveling around the circle. Well, we know that speed equals distance over time, and the distance it travels is the circumference of this circle, which is 2 times pi times r. Well, how long does it take the particle to go around the circle? Well, there's a special name we give to the time it takes something to complete a whole circuit, and that's called the period. And we denote that with capital T. You might remember this from the previous chapter on waves. So the circular speed of this particle is going to be 2 pi r divided by t. Now what's happening, or we can also choose to define an angle, because as the particle travels round the circle, it's sweeping out an angle delta theta. So as it goes from here to here, the angle that's being swept is equal to delta theta. Theta is the symbol for the angle, and delta means a change in. So we choose to define something called the angular speed, omega, to equal the angle swept over the time taken to sweep that angle. In other words, in symbol form, omega is equal to the change in angle over the change in time. So omega is the angular speed. Now we know for a complete revolution to go all the way around from here to here, we have to cover 2 pi radians. And remember, when you're working in circular motion, at least in this course, to use radians. So the angular speed is going to be the total angle swept, which is 2 pi, over the total time, which is still t, the period. So we have this expression for the angular speed, which you might remember from the waves chapter. And again, frequency comes up in not only in the circular motion topic, but also in the waves topic. And also angular frequency. Well, if you remember, the frequency is equal to number of cycles a second, which can be defined as 1 upon the period. And we also have the angular speed to equal 2 pi upon the frequency. Well, the only thing that differs these two numbers is the 2 pi here. So if I multiply both sides by if I multiply both sides up here by 2 pi, you see I get this thing over here equals the angular frequency, and this thing over here equals 2 pi times the frequency. So omega equals to 2 pi f is the relationship between the angular frequency and the frequency, if you like. Remember that the units of omega are radians per second. So now we're going to try and find the relationship between the linear speed and the angular speed. So if we look again at our circular path, here's the particle. It's gone from here to here along this line here. So the question is, how far has it travelled? Assuming it's got a constant velocity, we can define, remember, speed equals distance over time. So the distance it's travelled is equal to speed times time. So over this time, let's say it's taken a distance, or sorry, it's taken a time delta t to travel this distance. So therefore, the distance in terms of the linear speed is v delta t. But we also know, or we've also defined, that it swept out an angle delta theta over that same time, and remember that the radius of the circle is r. Therefore, this arc length, this is an arc of the circle, has length r delta theta. So this distance is also equal to r delta theta. So we can put these two things equal to each other. So we have that v delta t equals r delta theta. Divide both sides by delta t, those two cancel, and I get v equals r delta theta over delta t, which is this thing here is just the same as the angular speed. So we have that the linear speed equals r times by the angular speed.